So a biology professor reports that historically grades in his introductory biology course have been distributed as follows. So 15% of students get an A, 30% get a B, 40% get a C, 10% get a D, and 5% get an F. Grades in his most recent course were distributed as follows. So we can see what the students actually got. So the first thing we want to do is actually just want to go ahead and find what the sample size is. So it's 89, 121, 78, 25, and 12. If we add all those together, we get a total of students of 325. So now which test would be appropriate to determine if the professor's grades percentage are correct? So we have one categorical variable, the grades, with 5 different categories. So if we have one categorical variable with more than 2 categories, we want to do a chi-squared goodness of fit test. So the correct answer is C. So we want to see, could these occur if 15% get an A, 30% get a B, 40% get a C, 10% get a D, and 5% get an F? Are these reasonable to happen from a population that looks like this? So we want to know what's the expected count for B's in the class. So if this null hypothesis up here is actually true, how many of the students will we expect out of the 325 to get a B? All we want to do is take our sample size, multiply it by the proportion of students who get a B, so that's going to be 325 times 0.3, which is 97.5. So we would expect 97.5 students to get a B if these proportions are correct. So then we know what's the component of the test statistic from grade B. So our component is how many students actually got a B. I'm going to subtract what we expect to see, 97.5. We're going to square that whole thing and then divide by how many we actually expect to see. So if you work all that out, we end up with the component being 5.66. And then if the test statistic is 15.02, what would the p-value be? So it's called a chi-square test of goodness of fit because we want to use a chi-square distribution. So a chi-square distribution is like an F distribution. And that's a right skew distribution. We're going to mark where our test statistic is of 15.02. We need to know where our degrees of freedom are. Well, we have 5 categories. We're going to lose 1. So degrees of freedom are going to be 4. So we go to second, vars, scroll down to chi-squared CDF, because anytime we're finding a p-value, we're always going to be using CDFs. Our lower bound is 15.02. Our upper bound is some large positive number. Degrees of freedom are 4. So we need a p-value of 0.0046 or 0.005. So you want to remember that these are right-tailed tests anytime we're dealing with a right-skewed distribution. So for a chi-squared goodness of fit test, a chi-square test of independence, we'd never be able to do a two-tail or a left-tail test. Then 16 says, what is the conclusion at a 5% significance level? So our null hypothesis is going to assume that these stated proportions are correct. Our alternative hypothesis is going to say that they're incorrect. Well, if we reject the null hypothesis, we're going to say that we have evidence to believe that the stated proportions that the professor says students get isn't really believable based off what we see in the class. So we're going to reject the null hypothesis because our p-value is small. And then we're going to say there is sufficient evidence to claim that the stated proportions are incorrect. So the correct answer would be C.